In this video, we use what we know about non-negative matrices to study a random process. You'll see that the random process is built around a scenario that's a bit contrived. Still, it will serve to illustrate an approach that's useful in a bunch of different situations. Suppose that on any given day, I'm either mad, sad, or glad. Suppose further that whatever mood I happen to be in, I stay that way for an entire day. Let x of t be a random variable that takes a value of 1 if I'm mad on day t, takes a value of 2 if I'm sad on day t, and takes a value of 3 if I'm glad on day t. Now, let's say my mood from one day to the next shifts in a random fashion among its three states. Specifically, if I'm mad on one day, then I'm sad on the next day with probability 0.4, and glad the next day with probability 0.6. Alternatively, if I'm sad on one day, then I'm mad on the next day with probability 0.7, and glad the next day with probability 0.3. Finally, if I happen to be glad on a given day, then for sure I'm mad the next day. Overall, the network I've just drawn models my shifts in mood as a random process. Based on this model, we'll answer the following question. If you and I meet up someday, say several years from now, then what's the probability that I'm mad on that day? In mathematical terms, we want to know the probability that x of t is equal to 1 in the limit as t goes to infinity. Don't forget, x of t is equal to 1 corresponds to the event that I'm mad on day t, and we take a limit as t goes to infinity because we're thinking about a point in the distant future. Of course, we're taking it on faith that this limit exists, but as you'll see, we're okay on this point. To calculate the probability that x of t is equal to 1, we'll turn to the law of total probability. We notice that my being either mad, sad, or glad on the previous day, that is day t minus 1, corresponds to a mutually exclusive and exhaustive set of events. As a result, the probability we're looking for can be expressed as follows. Now, using the information from the network, we can write out the formula for the probability that x of t is equal to 1 like this. Notice that this recursive statement depends on the probability that I was sad on the previous day and on the probability that I was glad on the previous day. If we're going to turn the recursive statement into a non-recursive one, then we'll need to sort out these probabilities with recursive statements of their own. Turning again to the law of total probability and the information presented in the network diagram, we find that the probability that I'm sad on day t is this, and the probability that I'm glad on day t is this. We now have a system of three equations that can be represented in matrix vector form as follows. The advantage of writing the equations in this way, I suppose, is that it makes clear the fact that the recursive mathematical statement relies on a non-negative matrix. And it underscores the fact that we have an opportunity to apply our newfound knowledge about non-negative matrices. Our special new knowledge about non-negative matrices comes to us in the form of an extension of Perone's theorem. That extension applies only to non-negative matrices that are primitive. So let's take a moment and verify that the matrix and the corresponding model pass this test. The first thing we should do is verify that the model is irreducible. A quick glance at the network diagram reminds us of our assumptions and the fact that we can't understand the dynamics of my mood without keeping track of all three of its states. In other words, we can't reduce the model by dropping one of mad, sad, or glad and still track my feelings properly from one day to the next. So we put a check mark beside irreducible. We're good there. Next, let's run the check on path lengths. For every node, we're going to count the lengths of all the paths that begin and end on it. Then, we're going to find the greatest common divisor of these lengths. For node 1, we see that the lengths of the paths are 2, 3, and actually we can just stop there because 2 and 3 are prime numbers, which means the greatest common divisor we're looking for is 1. We find something similar starting and ending paths on nodes 2 and 3 respectively. And since the greatest common divisor of the lengths of all the paths for all the nodes is 1, we conclude that the matrix itself is primitive. This means we can apply the conclusions of Perone's theorem. Let's not forget that we're trying to deal with this recursive statement. We know that we can establish a non-recursive statement by applying the matrix at the center of our model, t times, to the vector that describes my initial mood. Thanks to Perone's theorem, though, we can say that this will tend to a multiple of the dominant eigenvector of the matrix as t grows. Moreover, this tendency has no dependence on my initial mood. So, let's turn our attention to finding that dominant eigenvector. We'll find the dominant eigenvector of our non-negative matrix in a rather circuitous way. We start by finding an eigenvalue using a little trick. It turns out that, because the columns of the matrix each sum to 1, the number 1 must be an eigenvalue of the matrix. We don't know at this point that it's actually the dominant eigenvalue, but let's put that worry on hold and just find an eigenvector associated with it. An eigenvector associated with the eigenvalue lambda is equal to 1 must satisfy this equation, which corresponds to this system of 1, 2, 3 linear equations. From equation 2, we see that v1 is equal to 5 over 2 times v2. We sub that into equation 3 to find that v3 is equal to 9 over 5 v2. If we choose to set v2 equal to 10 then, our eigenvector associated with lambda is equal to 1 is the vector 25, 10, 18. Notice that this eigenvector has only positive entries. So, by Perone's theorem, we can be sure it's the dominant one. Incidentally, that means lambda is equal to 1 must be the dominant eigenvalue as it's associated with this eigenvector. We know then that as t becomes large, the probability that I'm in any given mood corresponds to the entries of some vector that is itself a multiple of the dominant eigenvector. In this case, we use the fact that the probabilities here must sum to 1 to find the multiple of our eigenvector that best suits our purposes. Adding up the entries of the eigenvector, we see that their total is 53. So, for our purposes, we rescale the dominant eigenvector by multiplying it by 1 divided by 53. It follows that I'm mad on the day we meet up with probability 25 over 53, which is about 0.47. That's the answer to the question we originally posed. Though it's not part of the question we were trying to answer, I'll mention that we can interpret this final result as saying that, in the long run, I spend about 47% of my days being mad, 19% of my days being sad, and 34% of my days being glad. Let's recap. In this video, we analyzed a model of a random process built around a non-negative matrix. We verified that the conclusions of Perone's theorem could be applied to the matrix at the center of our model, and then we focused our analysis on finding its dominant eigenvector. we found that the entries of the dominant eigenvector, properly scaled so that they sum to 1, gave the probability that the random process was in the corresponding state in the long run. Once you've mastered the approach set out in this video, you'll be able to do a couple of things. First, you'll be able to use the law of total probability to construct a recursive, matrix-based model for a random process. You'll also be able to do the same thing, but starting from a network diagram. Second, you'll be able to provide an interpretation for the dominant eigenvector of a matrix at the center of your model in terms of the probability of finding the random process in a given state in the long run. Don't let watching this video be the only thing you do to learn about the application of non-negative matrices to the study of random processes. Read, try the exercises, participate in course activities. Those are all positive things. Maybe also try to come up with your own model of a random process. Maybe something more biologically compelling than my own shifts in mood. Study the process you devise with the same tools and see what amazing conclusions you can come up with all on your own.